Okay, we'll be starting momentarily. Okay, sorry about that. It's been quite a delay. Sorry, I was just like getting things ready. We're going to start now. This is just like probably the thumbnail that you see on this as well. And so we're going to be going to this textbook, Larson's Calculus. It's like, I forgot where exactly. Let's say 900. So 12.2, which is about differentiating and integrating vector valued functions. That's going to be like the main focus. And I made a video earlier about just vector valued functions in general, which was 12.1. And we didn't do any of the questions over there, but we did kind of like look over what all they were saying before that and read over the notes and well, I guess the lecture. So this will be similar. We might also just go over a little bit of what 12.2 is about, like just the topics and explain those. But the main focus is to just work on these questions, and there are a lot of them over here. One second. Okay, sorry about that. Yeah, so we're going to just be working on these exercises. In the beginning, we're going to be sketching some plane curves represented by the vector valued function, and then sketch r sub t0 and then r prime t sub 0. Position the vector such that the initial point is at the origin, initial point is at the terminal point. What is the relationship? Okay, so there are like 6 of these, and they're probably all going to be pretty similar. So maybe we'll do a few of them. Maybe we'll do all of them, depending on how easy they seem to be. But yeah, we'll probably only do a few of them. Okay, so let's just place this here and get started then. Give me one quick second. Just like once we get into the once we do this, once you do more of these questions, it'll get a little easier. And so just bear with me until then, please. Okay, all should be good now. So let's graph the first one. You just draw a rectangular coordinate system, and actually you don't even have to do that. This is just, so if you let y equal t, we can see that x is equal to t squared, so that's just y squared. And so this is going to be a parabola. So we'll just draw it out like this. This is the y-axis, this is the x-axis, and so this parabola would be a horizontal parabola, and so it would look something like this. Okay, something like that. When t sub 0 is 2, you're going to have x is equal to, so you're going to have time, sorry, you're going to have time is equal to 2. Actually, to be very specific here, I don't think time should be negative. I don't think t should be less than 0. So you would only have this part in that case. Point is, what matters though is t sub 0 equals 2, and that's going to be when x is 4 and y is 2. So that's a point over there. What else are they asking us for? They're asking us for r prime t of 0. So what is r prime of t? That's just going to be 2t comma 1. And when you put this in at, oh sorry, no. So this is a parametric equation. The vector that they want us to sketch, I want to put that in a different color. We'll put it in like light yellow. That vector will look like this because you're starting at the origin. You're going until there. And what is this going to be? Well, this is a vector. When you plug in t sub 0 equals 2, that's going to give you 4 comma 1, right? And so 4 comma 1 is going to be the vector that we draw out now. 4 comma 1. So okay, position the vector such as the initial point of r sub t0, r of t sub 0 is at the origin, initial point of r prime is at the terminal point, blah blah blah, and the curve. Okay, yeah, so that'll just be 4 more in this direction, 1 more over here, so it'll end somewhere there. We can do this in blue, and that would look something like this. I don't really think there's any particular relation over here. What's the relationship between, oh well, no, that's the slope at this particular instant, right? Like at this particular instant, that's the slope of this. Not drawn perfectly, but that's what it would be. I think that's what they're trying to get at with the question. We can try, let's try one of the harder ones then maybe. Let's try something like 4, right? Looks a little bit trickier at least. We can also try 6 after this, but I don't want to do like all of them because there's so many other questions to be done as well. So let's do number 4. So here we've got y, here we've got x, and let's see. So x is going to be equal to 1 plus t. Well, okay, let's just think about it like this, right? X equals 1 plus t, y is equal to t cubed. So that's x minus 1 whole cubed. And that's going to look just like this, right? That's what it would look like, roughly. And then we need t to be greater than 0, so x should start at 1 over here, and it should then look something like this, I guess. Right? It should just be this section. Doesn't really matter. This is what we have right now. When we plug in t sub 0 equals 1, which is what we're asked to do over here, that will be the point 2 comma 0. Oh wait, sorry, did I 2 comma 0? Yeah, no, sorry, it's okay. It's 1 comma 1, 2 comma 1. Okay, I don't know what I'm saying. I x is equal to 2, so y is going to be equal to 2 minus 1 cubed, which is 1. So this is 1 comma 1. And so r of t sub 0 is also going to be that. Sorry, I'm just like this. Okay, what would the slope be? Well, for the slope, you just need the derivative. So what is r prime of t sub 0? Well, what is r prime of just t? That's going to be, you've got 1 plus t, take the derivative of that, that's just 1, and this is 3t squared. So r prime at t sub 0, sorry, low battery. This would still be 1, and then this would be 3. So 1 comma 3, which would be something like this. And again, same idea, this is just the slope at that instant. Okay, they're all pretty much the same at this point. 6, you'd have the vector 1 comma 1. That would be, you go from the origin to 1 comma 1, and then the derivative would just be e to the t, and then e to the 2e to the t. So it would be 1 comma 2. So to go It'll be like one in the I direction and then two in the J direction. That's what it would look like. You can draw it out and try it for yourself. But I don't want to waste too much time on these earlier questions. The more interesting ones come later on. This has a graphing utility, so I'm not going to do that. Same with 8. Usually they're in pairs, so 7 and 8 are the same thing. Let's try this one. So we'll do both of them, or maybe just one. We'll see the one that looks more interesting. Actually, I know how to graph the first one. That looks to be a helix, and then the second one is like it's like a translation of a parabola moved up 3 units in the z direction. Give me 1 second. It's on the xy plane, and the entire xy plane has been shifted up by 3. Okay, it's charging now, so that's good. Yeah, let's continue now. So the first one, the 2 cosine of t and the 2 sine of t, you can kind of convert that. You can say x equals 2 cosine t, y equals 2 sine t, then x squared plus y squared is equal to 4. And that's, of course, a circle. So that's one way to think about it. And then at the same time, t is going to be increasing as you're tracing out the circle. So you're going to be making a helix. And that's a little difficult for me to draw. So I'll try to do it at least. So let's just start. When t equals 0, you're going to be 2 in the I direction and nothing in the j direction. And then you're going to go this way, this way, this way, this way, this way, up, 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 up. It's like really forming a sort of spiral around this. And I'll try my best to draw it. It's not going to come out the best, maybe. Let me just verify that the direction is correct. Yeah, so it should go this way. So let's try. Up, 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 up. So just imagine that it's going up like this, right? When t is equal to 3 pi over 2, well, that's going to be over here, right? So the z is going to equal 3 pi over 2. X is going to equal what? Well, it's going to be 2 cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so that's just 0. And what is y going to be? Well, negative 1 is sine of 3 pi over 2 times 2, so negative 2. So the point here would be 0, negative 2, and then 3 pi over 2. So they're asking us to sketch that vector. All we'd end up doing is drawing a vector from the origin to 0. So 0, negative 2, 3 pi over 2. So maybe like this point over here. That's what the first part would look like. Now what about r prime of t sub 0? What is r prime of t? Well, I'll do it in component form like this. That's easier for me. It'll be negative 2 sine of t. And then over here it's going to be 2 cosine of t. And then the t here just goes to a 1. Right? Now, so let's evaluate that. We don't have to graph it. This would just be a circle, but maybe a slightly like the direction, the orientation of the circle would be different. That doesn't really concern us, so because does it? Yeah, no, it doesn't concern us. We just need to sketch the vector of r prime of t sub 0, and all this is going to be is plug in 3 pi over 2 again. What is negative 2 times sine of 3 pi over 2? That's just 2. This is 0, this is 1. So you trace out 2, 0, 1. So something like this vector over here. Okay, so that's all we do for question 9. Let's try question, this is question 9. Question 10. What would this graph look like? Well, we have x equaling t, y is equal to t squared, so that's just x squared. And then z is just stuck at 3 halves throughout. And so you can just draw this on an xy plane and then pretend that it's been shifted up. So that's kind of what we're going to do. Y is equal to x squared. So that would just look like that, right? And I'm guessing x has to be positive. Okay, well, it should look like this then, because it's the z value is 3 halves. So Let me just try it again, try to keep it a little realistic. If t is allowed to be negative, it'll go like this. It's basically on the xy plane. It's on z equals 3 halves. So it's just been shifted up by 3 halves units. That's what that would look like. When you plug in t sub 0 equals 2, you're just going to have 2 comma 4 comma 3 halves. That's going to be r of t0, r prime of t0. Let's try to do this in our head. The derivative of t is always going to be 1. Derivative of 2t of t squared is 2t. When you put in 2 for t sub 0, it's going to be 4. And then 3 halves is a constant, so that's 0. So one of the vectors would be this, and then the other one would be this. And we don't need to graph them out because it's hard to do that. But the point is that we understand how to do that. Okay, all of these now are just derivatives. So we're going to do those. We're going to do these very quickly, hopefully. Going to blitz through these. Okay. I'll try to be a little neater as well. Maybe change up the colors that I'm using to make it easier on the eyes. So 11. Well, we just do it component wise, right? And so r of t, r prime of t is going to equal, we're going to have 6, we're going to have negative 14t, and then we're going to have 3t squared. Boom, done. 12 r prime of t. So the first term is going to be negative 1 over t squared. The second one is just going to be 16, and then the next one is going to be t. When I say term, I mean I should be saying components instead. A is a constant, so we don't really care about that. What we do care about though is the fact that, so we have to use the chain rule over here. So it's going to be 3a, then we're going to keep our cosine squared of t, but we also multiply now by the derivative of cosine of t, which is negative sine of t. You can now, I mean, you can take out a cosine t and a sine t, multiply them together, you get sine of 2t divided by 2. You can do those sorts of things. I don't think there's a need to do that though. Just leave it as is. Let's take a look at the second component. Second component is going to be very similar. 3a sine squared t times the derivative of t of sine of t, which is cosine of t, and then the last one is 1k. The derivative of 1 is 0. So we're done. 14 for root t. So okay, let's write this again. For root t, the derivative of root t is 1 over 2 root t. So it's going to be 2 over root t. You can rationalize that if you want. T squared root t, well, that's nothing but the derivative with respect to t of t to the 5 halves, which is equal to what? That's 5 halves t to the 3 halves, right? So that's going to be the second component. Not the neatest way of writing it, but that's it. The last one is a little bit of a trick. There are different ways to do it, but I think the easiest one is to just notice that natural log of t squared is nothing but 2 natural log of t, and so it's going to be 2 over t. You'd get the same thing if you applied the chain rule, but it's just easier. You can just use the logarithm properties directly and simplify your work. What about 15? This one seems a little easier. There are also only 2 components this time, so just make sure you're putting in the right components. In case if it were like j and k, you wouldn't want to put just 2 components. You'd have to put a 0 for the I component. That's not a concern here though. It's e to the negative, it's negative e to the negative t, and then 4 will just give you 0, right? The derivative of 4. What about 16? Over here, what are we going to have? Well, sine of t has a derivative of just cosine of t. And now when we do this, we're going to get minus cosine of t plus t sine of t from the product rule. Yeah. And then cosine of t is going to give you negative sine of t plus sine of t. And then you're going to have a plus t cosine of t. So, okay, the plus and the t's are looking very similar, so sorry about that. But we'll simplify them. And you'll notice that cosine of t and negative cosine of t cancel out, leaving us with t sine of t. Over here, we're going to have t cosine of t. And then here, we're going to have 2t. You can also take out a t from the whole thing then. And what do we get now? A very nice, easy graph. And there, done. Okay, next one, 17 and then 18 after that. I'll do these like over here on the side maybe. 17. Okay, well, very, very similar to what we just did. Right, it's easier than that actually. It's going to be sine of t plus t cosine of t for the first component. The second component will be cosine of t minus t sine of t. And then the third component will just be 1. Done. 18 r prime of t is equal to, let's write down the components. Arc sine of t is I think 1 over the square root of 1 minus x squared. And of course the derivative of 0 is just 0. So done with that. That was, that's quite a few problems that we just did. What is that? 8 questions. They were all pretty simple, like basic differentiation, except you're just doing it for each component now, right? Like that's how you do it with vector valued functions. Some of these other ones are a little bit harder though. Like yeah, like these ones, I don't think they're necessarily harder, they're just a little bit lengthier, and so a little bit more annoying to deal with. But it's not really I don't think it should be much of a problem. It's just more work, but the work has not gotten inherently harder or anything. It's still the same difficulty, still the same type of stuff that we're doing. I want to do it over here so that there's some space, and we will switch colors this time just so it's a little nicer to look at. Okay, so we'll take like a pink color for this. Let's begin by, so I mean we can just do each question on its own, or we can find r double prime. Okay, first thing, we do need to find r prime of t, then we need to find r double prime of t, and then we need to do the cross of the two of them, right? So for each of them we basically do need to find the first and second derivatives and then do a little bit of math after that as well. So what is r prime of t going to be for the first one? It's going to be 3t squared, and then you get just a t. So r double prime then, let me just make sure that everything I'm doing is like showing on the screen. I think it is. Thank you, Ishan. Thank you, Harish. I just opened the chat right now because I came back to the computer, like to this screen, but yeah, thanks for your support. Okay, and over here, you're just taking the derivative of these now. So you're going to get 6t, and then the t reduces to just a 1. So that's the first two steps. Now we need to do the dot product. The dot product isn't too difficult. We just multiply the respective components and add them up. So we're going to have, it's going to be like this. 18t cubed plus t. That's all it is. Other ones will definitely get a little bit messier to work with, but this is like the key. This is all you have to do. It's not super difficult, right? So for now, if you do the same thing for 20, we're going to have, again, it's just I and j, and then later on we're going to have I, j, and k. But that doesn't make it much more difficult because it's just a dot product, so you're just multiplying terms. So it's not too much more work. This will give you 2t plus 1, and then 2t minus 1. Our double prime of t is just going to be 2 comma 2. And so if you do this now, you don't even have to actually perform all the math yourself. You'll get a 4t plus 2, 4t minus 2, so you're going to get a total of 8t. And with that, you're done. What about 21? R prime of t is just going to be negative 4 sine of t. And then the second component is going to be 4 cosine of t. So our double prime of t is going to be, oops, 1 second. Negative 4 cosine of t, and then you're going to have negative 4 sine of t, right? And if we do this, what we're going to get is So let's just do the math, right? Like, I think it's going to be 0, but I want to check that. What are we going to get? We're going to get 16 sine t cosine of t plus negative 16, so it's going to be minus 16 sine t cosine t, which is 0, meaning that this is what we have. R prime of t is perpendicular to or orthogonal to r double prime of t. I think this is going to be one of the properties that we discuss later on as well. So look out for that. Question 22. 22 is the last one where we've only got two components. So there's just going to be a little extra work from here on out, but not like nothing unmanageable. R prime of t is going to be what? 8. So negative 8 sine of t. And then the 3 sine of t will become 3 cosine of t. So it's just like a lot of the same old stuff each time you do this. Hopefully you've got like good experience with just differentiating, because it's obviously going to make your work a lot easier here. We get 64 sine of t, and then minus 9 sine of t cosine of t. So this is going to give you 55 55 sine of t cosine of t, or 55 over 2 sine of 2t. That's the same way. That's another way of writing it, because sine of t times cosine of t divided times 2 is sine of 2t, right? So maybe it's a little simpler like that. It's debatable. I don't think you have to be doing all that, but it's it's a personal choice. I want to just copy paste these questions lower so we can access them easier. Right here, maybe a little bigger than that. Okay, so obviously the quality got sacrificed there, but that's not a big issue. We also switch colors now. We might go to like a nice like dark blue, but still visible. So same exact procedure as what we were doing earlier for 23, for example. R prime of t now is going to have three components, so right, and the components aren't. It's not like we're doing really difficult work with the differentiation here. It's still the same type of stuff. If anything, it's like easier, but just be a little careful. Make sure you do put all three components, right? And yeah, over here you can see this will just become t, and so 23 gives us a really nice and easy answer. We're going to get t plus 1/2 t cubed. Let's try 24. 24 also doesn't seem that bad actually. 24 seems, I think we can, let's do 24 in our head actually. The second derivative of each of them in each direction is going in I, j, and k directions are all going to be 0. So you're going to have 1 times 0, 2 times 0, 3 times 0, which is just 0. And so from that we can tell, I mean, they aren't asking for this, but might still be useful to just write down that this is the case. They're orthogonal. If you aren't sure about how we can go from the cross product, the dot product being 0 to this, that's something that was covered in chapter 11. And I don't want to go, we'll probably get to it later on. Like if you have questions, just like ask in the chat or something. I don't think it's super important though. Like, I mean, you hopefully you're already familiar with that. If not, I think it's not too difficult to learn on your own. I don't want to go into that right now because there's a lot of other stuff to do. Like just a quick precursor. We're still only on, I've already skipped a lot of questions and we're on like what, 25. So there's a long, long way ahead. There are like 87 questions here. We're not, some of them are easier than others. Some of them we don't have to do necessarily, but we should be doing a lot of them. Okay, 25. So r prime of t is going to be, this is going to be a long one, but I think we did the exact same question earlier. But since it's like not difficult, we'll just do it again. Cosine of t is going to give us negative sine of t. Then we have a plus uh, t cosine of t. I wrote it badly. And then we have a plus sine of t. So this is the first component. The second component is going to be cosine of t minus cosine of t plus sine of t, I think. Sorry, plus t sine of t. This is just on the product rule. And then the last one is 1. Before we move on to the second derivative, it would be prudent to like simplify this, right? The negative sine of t cancel out, so we've got just t cosine of t. over here we have just t sine of t, and then here we've got just 1. So first part is done. R double prime of t, we're going to have t cosine of t minus sine of, no, 1 second, 1 second. Cosine of t minus t sine of t for the first component. Second component will be sine of t plus t cosine of t. Third component is 0. Perfect. Now we need to multiply, and I think we will probably see, yeah, we'll see very nice cancellations, actually, very nice ones. So let's just do the math, and then you'll see that with me. We get t, so I'm going to write it all out, and it will look very messy, but like pause the, well, you can't pause it. Mute me, and then like just do it on your own and see, and then hopefully we'll get the same answer. I'm not sure if I'm correct. I just think that this can be simplified, and I'm sure the question won't be like, I'm sure there won't be a very messy answer to this. I'm not going to write the last term because there's a limit on the space we have, and it's obviously 1 times 0, which is 0. But over here, you're going to see we have a t cosine squared t minus t squared cosine t sine t plus a t sine squared t. You might already have noticed what's going on. Plus t squared sine t cosine t. And this cancels with this. Now we're left with t times, I'll scroll down, I don't know if you can see, t cosine squared t plus t sine squared t. We can factor out a t from this, which leaves us with just t. Right, so very nice resolution to a otherwise pretty lengthy and kind of annoying problem. But it wasn't like inherently difficult, right? It's just the same stuff. No, nothing new was learned over here unless sine squared t plus cosine squared t equals 1 is new to you, which shouldn't be. Let's move on to 26. I'll just copy down the question. This one I haven't done this one myself. Actually, I should have done this because it was in my homework, so maybe I did the wrong one. I don't know. But okay, r prime of t, what's this going to be? It's going to be negative e to the negative t. Then we're going to have 2t, and then we're going to have secant squared t. Uh, yeah, that's correct, right? Yeah. So r double prime of t, well, the first one is just going to go back to e to the negative t, right? That's nice. This one is going to be 2. And then this one, what's the derivative of secant squared t? Well, we can, I mean, there's probably a nicer way to go about doing this, but let's just do the less nice way maybe. 2 secant of t times the derivative with respect to time of, with respect to t of secant t. The reason I'm doing this is because I'm pretty sure I remember that the derivative of secant t is just secant t tangent of t. If I'm wrong, then obviously then that makes things worse, but I think I know what it is. So then, which means it's like not super difficult, it's just a little messy, but it'll be 2 secant squared t times tangent of t. Okay, now we're doing r prime of t dot r double prime t. So that's going to give us negative e to the negative 2t, because it's like squared. Then we have a plus 4t plus 2 secant to the fourth t times tangent of t. So unlike the last question, this one really does not have a neat and nice answer. It's a very messy one. Uh, can you make simplifications? Possibly. Like secant to the fourth of t, you can probably write that, you can write that as tan squared t plus 1 whole squared. But I don't know how that would like really help, right? It's probably not adding anything meaningful. Regardless of what the answer is and how it should be represented, though, we're done now. So we finished this set as well. Um, okay, 2 more graphs over here. We can just do this instead of copy pasting, we can just do it here. Okay, like just, right, if we think about it, let's do 28 first. Oh well, no, okay. We're going to skip this because we've already found lots of unit vectors. I mean, sorry, we found lots of r primes and r double primes. It's the exact same thing except you're normalizing it. You're dividing by the magnitude, and to do that, you just find each of the components, take the square root of the squares of the sum of the squares of each component, which is just like messy, and it's just a lot of. It's like not particularly nice to work with either, right? So I don't see the point in doing that. Let's move on to this instead. And this is where things get a little bit more interesting because it's kind of talking about a smooth curve when a vector valued function is smooth, which is like the vector analog to the scalar concept of differentiability. I think that's probably, yeah, that's kind of a good way to think about it, I think. I'll show you what I mean. I'm just saying words right now, but I'll show you what I mean. We'll do a few examples. And for most of these, like the answers aren't going to be like long. So like, we just have to write like intervals. So we can just write it directly on this section over here. First one, r prime. So, okay, for a lot of these, you'll still have to calculate this, but it's not too difficult, right? This is just 2t, 3t squared. The derivative is defined at all points. What? So that's the first thing, right? Like, first of all, r of t or r of theta, as you see in these ones, it should always be it should be continuous, right? You're not going to be smooth if you're not continuous. Like if you just go like this and then you jump up from here, there's a jump discontinuity, just like with scalar valued functions. You can't have that in a vector valued function. So you should be continuous. I'll be more specific. R of t is continuous. You also want to make sure that r prime of t is continuous, right? Meaning that there's, well, not continuous, that it exists, right? If it exists, that means that there's one definite direction, one definite tangent vector, exactly one tangent vector to r of t. That should be the case, and then r prime of t should not equal zero. If it's equal to zero, think about this, right? That has no direction and it's got no meaning either, right? Like what is a first of all, it's not zero, it's the zero vector, so we should write it like that technically. But the zero vector, like okay, the vector, if you look at a three-dimensional space like this, the vector I is like that, the vector j is like that, the vector z is like that, right? I is just z is 1 0 0, right? So two of the things are zero, but there's still meaning, right? You're moving one unit in the x direction. J is 0 1 0. Even though z are both zero, you still got some meaning, right? But if you have the zero vector, which is 0 0 0, how can you even draw that? You can't. It's just a point, right? And if that's your slope, right? Think about what this represents. This represents a slope. If the slope is zero, it's like similar to a function, but it's also not similar to a function in the sense that like a scalar valued function, because like it's not going to continue from that, right? There's no definite tangent vector, and that breaks the idea. That means that there's essentially a cusp or like this type of thing. Cusp, there's another word for it as well. I forgot what it is. But okay, so I'm just like saying a lot, but this is really what we have to focus on. These are the three criteria, and you can see for the first one, just based on this, it's seems to be always working, right? It's a very nice, very easy thing, and you'd be inclined to say all real numbers, right? Because it's if you were dealing with a real valued function, that would certainly be the case, right? It's defined for everything. The derivative is defined for everything, but at the point when t equals zero, you're going to have um. Is there another value for this as well? I don't think so. No. At t equals zero, you're going to have 0 comma 0 for r prime of t, and so we that cannot be included. So we can just write it like this. Zero does not work, right? That's the only important consideration here. Okay, R of t for question 30. Sorry, I know I kind of went into like an explanation mode over there, but I think it'll be helpful for the other ones here. Okay, so what is R prime of t? First of all, this is not continuous everywhere. The 3t isn't an issue, but this tells us that t cannot equal 1. So we'll keep that in mind. What does R prime of t tell us? Well, it's going to be like this, I think. That's the first component. The second component is 3. Luckily for us, because this component is 3, we don't have to worry about r prime of t ever becoming the 0 vector. This, first of all, this can't ever become 0. But even if this could become 0, this is never going to be 0, right? The 3 is 3. That's not going to change. And so we're fine. There's nothing to worry about there. But obviously, t cannot equal -1. Also from here, t cannot equal -1. So make sure you don't write -1 as part of the set. So this one I think should be all real numbers except -1 for t. You can write like t belongs to this, right? Or like t such that t belongs to that. But we're not going to do that each time because there's obviously limited space. Let's try the third one now, 31. I'll let's see. So it's uh, what's the best way to do it? Okay, so let's start with the fact that we're not dealing with t, it's theta now. So just make sure to do that to account for that whenever you're writing. But the function itself, r of theta, is always continuous, right? Because cosine cubed of theta, sine cubed of theta are both continuous. So now the matter is of its derivative. So let me just rewrite the question here entirely. It's 2 cosine cubed theta and then 3 sine cubed theta. So if you take the derivative, what are we going to get? We're going to get r prime of theta is equal to, over here we're going to get 6 cosine squared theta times negative sine theta. It's messy, I know, but okay, we'll do it like that. This one will become 9 sine squared theta cosine of theta. And now the job is to see when they're is this continuous? Again, it is continuous at all points, right? I mean, it exists for all points, and it's continuous for all points, I think. What the issue is, what about when r prime of theta equals 0? Does this ever happen? And the answer is yes. So let's show that. You're going to have -6 sine theta. I'm writing this in a very deliberate way so that I think it'll be of some use. Sine theta. So I'm just breaking up this stuff here a little bit. Okay. You can do a few different things now. You can check, first of all, are these things ever going to be equal to 0? And it's a little messy if you're dealing with 3 different terms. So we can shorten this to -3 sine of 2 theta cosine of theta. And then here we've got 9 halves sine of 2 theta sine of theta. For either of these to be 0, over here you either have sine 2 theta equals 0. Over here you have sine 2 theta equals 0. That should hopefully give you a clue. Or you have sine of theta equals 0. Over here you have cosine of theta equals 0. We know that sine squared theta plus cos squared theta is 1. So these two can never be true simultaneously. So that we can scrap that. Well, okay, we shouldn't scrap. Technically, this and this can be together, but we don't care about that because we know that this is the exact same for both of them. So anytime sine of 2 theta is equal to 0, that all that means is essentially sine theta is 0 or cosine theta is 0. And if that's the case, uh, r prime of theta is going to be the 0 vector. So when is this true? Well, let's find out, right? This means 2 theta is equal to pi n, where n belongs to the two integers. So theta is going to be pi over 2n, where n belongs to the integers, right? So you can also, so the answer to the question would then be all real numbers except, actually, except theta such that theta equals pi over 2n, where n belongs to the real numbers. I don't think that you're supposed to make, I don't think you're supposed to abuse this notation like this, but it's all good. You get the idea. And yeah, that's it. So long-ish question. I'm not going to copy the answer there. Obviously, it's pretty lengthy, but hopefully you get the point now, right? Like it can seem like a perfect function, in the sense that a perfect vector value function in the sense that it's fully defined, so is its derivative, but it can never equal 0, right? And that's usually like the trickier part of these questions. Let's move on to 32. 32 isn't too difficult. Let's take a look. R of theta. And okay, so another quick note. You might wonder why I keep writing it like this, like R prime of theta, R double prime of t. Why I keep putting this arrow? I have to. Like technically, like the reason they aren't doing it is because they're doing it on print and they're instead putting the bold face. And putting bold is fine, but I'm not going to like sit here writing R like this each time, right? So it's just easier for me to put an arrow. But it does make sense. The reason I'm doing that is because this is a vector, right? Like just like when you write U cross W or U cross V or something, you put these things to indicate that they're vectors, right? Otherwise, you don't know what you're dealing with. So there is a reason for that. It's and same thing with the zero vector. It's this is not equal to this, right? So there's these small things that I'm doing them for a reason. If I'm making mistakes with anything that I'm doing, please do let me know because it's more than possible. I'm sure I made several mistakes already in the course of this live stream, but hopefully not on this question. So r prime of theta is going to be, just differentiate. You're going to get 1 plus cosine theta. That's always continuous. First of all, this is always continuous. I know domain restrictions from in either of those. The right hand side is sine of theta. How would this work? Well, 1 plus cosine theta equals 0. Is that true? And then sine of theta equals 0. They both have to be true. Now, is it, when you're writing conditions like this, I don't know, like, is it like, would you write it like this or like this? I don't know which one it is. I'm pretty sure it's this. I'm pretty sure this is what you used to say and, meaning both of them have to be true. And wait, did I do something wrong? 1 second. No, this seems right. Okay. Yeah, the point is though, like, just make sure you're doing this stuff correctly. If you have sine of theta equaling 0, what does that mean? Like we saw, that's just pi n, where n belongs to the integers. What about this? Over here, that this simplifies to cosine of theta is -1. And that is true at, let's draw a quick unit circle. It's true right here, right? That's at pi. Then it'll be 3 pi. Then it'll be 5 pi. Um, and so, yeah, that's only going to happen for odd multiples of pi. Right? Sine of theta equals pi here and here, but this is over here cosine is 1, and so you'll get 2 comma 0. You won't get 0 comma 0, which is the 0 vector, which is what you need, right? So okay, the point is it's just 2n plus 1 pi where n belongs to z. It's all real numbers except this. That's a 2 over there. Okay, next one, 33, 34. Do we have to do all? I don't think we have to do all of these. Let's try some of the more fun ones. Let's do 38. 38 seems like it'll be nicer because I really don't want to do all of these because there's a lot of other stuff. Like all the integration is still there. Right? That still has to be done. So let's move on over here. R prime of t is going to just equal. Okay, well, before we do that, let me use a different color, label where we are, and then proceed. Just so we're like rigorous with this. So we're now on this question here. We know R of t. I'll just write it all out. Root ti. I'm not going to do all that. I'll just put this instead. Nice and easy. T squared minus 1 and then 1/4 t. Okay. This gives no domain restrictions. This gives no domain restrictions. This does. We know that t has to be greater than or equal to 0. And that's the first thing. Let's move on from there. What about the rest of the stuff? What's the derivative of this? R prime of t. We're going to have 1 over 2 root t. I think we discussed this exact derivative earlier. This is going to be 2t. This is going to be 1/4. Beautiful godsend over here. Actually, no, that's too dramatic. 1/4 is obviously never 0, meaning r prime of t is never going to be the 0 vector because this is always 1/4. So that's fine. We don't need to worry about that. 2t still gives no domain restrictions. Neither does this. This does, though. It's a very small, subtle one. We cannot have t equaling 0. So when you combine these, you get t is just greater than 0. And that's it. So a long question, but remember, they're not asking us to do anything fancy. They're just asking us to find when it's smooth. And there are 3 conditions for that. The first one is easy to see. The second one is easy to see. Third one is a little bit trickier, but here it's very easy to see. So we're done. Actually, let's see if. Sorry, can you hear me? Let's see. I'll just check on my phone because I'll play it over there and check if it's loud enough. I'm getting a comment about low audio, so I'll see if I can like, fix that somehow. I don't know. Yeah, am I on the right account? Give me 1 second, please. Wait, I'm like I don't know how to check something that's going on right now. I don't know if I'm even on the right account. Huh. Give me one more second, please. Okay, let's see. Can you hear me? Okay, let's see. Okay, it seems fine on my phone, so maybe it's just on your end then. Uh, because other people seemed like they were fine as well. So I don't know. It's working on my phone. Maybe it's like on your end, or just like check if your audio is on and everything. But I will try to speak a little bit louder from here on out. But yeah, well, without further ado, let's head on over to the next section. So after 38, okay, these are very long. We're not going to do more than it's only two questions, so we'll do one of them perhaps. We'll do the first one. That looks nice and easy. The second one is like this is a helix, and this is some sort of inverted helix maybe, or like maybe it's still a type of helix. I don't know. But we're going to do one of them. It's lots of parts. That's why I don't want to repeat it and do it a full second time. But if it's like very fun and if it seems that we're enjoying it, we can do it a second time. So I'll just shrink it down and see. Not a very hard question, I think. It's like some of them are very easy. Like we've done so many first and second derivatives that should be like second nature by now, hopefully. If it's not, that's normal. I don't think it's a problem. It's fine. Let's we take a different color for this. Let's take violet. I don't think we've used that yet. R, so okay, A is just R prime of t, and that's very simple. It's 1, 3, and 2t. So done with that already. B is not going to be any harder than that. It's just, actually, it's even easier. It's 0, 0, 2. So, yeah, that's not bad. What about the other stuff? Oh, okay, we need to use properties of the derivative. I don't know what they want us to do with that. The derivative, so this is just derivative again. It's a different notation. Maybe not, it's not like this one or prime notation, right? It's different, but it's the same thing, so it's not nothing special. This doesn't mean anything special. It's just a derivative. And I believe the formula went, my teacher at school makes me put two dots on top as well because he's from Turkey. But yeah, I think this is the formula. Unfortunately, the formula doesn't really seem like, I think it's probably easier to just not use that formula because it's, think about it, you have to find this, do a dot product with this, find this, do a dot product with this. It's a lot of work when instead of that, you can just directly find the the dot product, and that would probably be easier, right? Like that's just a little bit more straightforward maybe. So let's go ahead and do that because look, as long as you get the right answer, you're fine, right? There's nothing, doesn't really matter what you do. So let's just find r of t dot u of t. What is this going to be? It's going to be 4t squared plus 3t cubed plus t to the fifth, which means the derivative of this is nothing but 8t plus 9t squared plus 5t to the fourth. Messy answer, and it's done. And if we did all of this, I'm sure that wouldn't be any faster. Like this is literally one 2 lines of work maximum, and that would just be a lot more. The Okay, let's find u prime of t, because obviously that seems to be a recurring theme here. What is u of t? U of t is right there. So u prime of t, we don't have to find it, but it might be useful nonetheless. That would just be 4, 2t, and 3t squared. So if you're doing 3r of t minus u of t, and you're taking the derivative of that, it'll just be 3r prime of t minus u prime of t, which is, that's going to be just like this. Right? You're just doing it with components. Everything here comes down to components. I hope I'm doing this right. It's possible that I'm doing this entirely wrong, in which case I hope someone will point out my mistake. But I think this is it, right? This should be correct. So pause the video and see if you need. But I think that's correct. Same thing with r of t cross u of t. R of t cross u of t. Actually, I know there is a formula for that. It's just that I kind of forgot. We can scroll up and take a look. That's nothing wrong with that. They had a list of important formulae here. Okay, it's the same thing as a dot product except you're crossing. But again, like, why would you do that, right? You have to think about it. You have to do 2 cross products with derivatives rather than just finding 1 cross product and then differentiating at the end. So that's probably, the easier thing to do, and that's what we're going to do. This is D, by the way. Let's move on to part E. So R of T is, what is it? Oh, it's right there. So okay, let's just draw it out. So there's going to be an I, there's going to be a J, there's going to be a K, T, 3t, and t squared. This is 4t, t squared, t cubed. So it's not going to be the prettiest of expressions certainly, but it's fine. So we're going to have 3t to the fourth minus t to the fourth minus j times, what do we get here? T to the fourth minus 4t cubed, right? And then plus k. What do we have here? We have t cubed minus 12t squared. Wonderful. Now we've got this. Now all we have to do is take its derivative, right? That's it. And so that's going to give us, so okay, let's rewrite this first, just so it's a little easier. It's going to be, so I'm going to be a little cheeky here. We just distributed the negative sign here. That's all I did. That's why it looks a little different. I also don't want to write the I, J, K, everything again, so I just put it like this. And now this is easy. 12t squared minus 4t cubed, 3t squared minus 24t. All done, and that's part E. What about part F? Part F is the magnitude of R of t. Now let's see if there is a property for that, because no, there isn't. So we actually have to like calculate and figure it out, which doesn't seem appealing to me, but we'll do it. So let's zoom in and take a look at that more. So the magnitude of R of t, what is that going to be? That's going to be the square root of t squared plus 3t squared plus t to the fourth. Okay, so what does this become? So this is the magnitude of R of t, by the way. So let's simplify this. And you'll notice some nice stuff here. We get 4t squared plus t to the fourth, from which we can take out a t, specifically an absolute value of t, but at the same time, because t is greater than 0, we don't have to do that. We just know it's t, because we're given that t is greater than 0, and then we have t squared plus 4. I think there's an integration question based on this after this as well. But whether that's the case or not, if all you have to do is differentiate this, you can like, just do that pretty easily, I think. Um, hmm. Yeah, so well, you just differentiate it. You don't even have to take it to this form. It's probably easier to just go and do it from here actually. So it's going to be 1 over 2 times the square root of, this is all from the, oh, it'll simplify nicely, I think. So we get 8t plus 4t cubed, not 40, 4t. And so the 2 cancels out, so we get 2t cubed plus 4 divided by t times the square root of t squared plus 4. There's a t over here, by the way, sorry about that. And then this is just 2t squared plus 2 plus 4 over t squared plus 4. So that's it. It's again, it's not the prettiest of answers, but it's definitely better than what you might have expected at first. And I'm sure it's, I don't know if there was any other way to do that anyway, right? I think that's just the most convenient and legitimate way of doing it. Anyway, yeah, that was one question. I don't know how long that took, but certainly longer than you should be spending on any of these questions. So let's move on now to these. Okay, sorry, we did that. Find this and this by differentiating and then applying. It's just more practice of the same stuff, really. I don't think we need to do that. It's actually kind of boring. I mean, not boring. It's just like very time intensive, and um, it's not really going to be of much value, I think. Let's do this. This is at least an interesting question because you're finding the angle theta, right? And that's somewhat, at least somewhat unique of a question. We won't do both of them. I think we can just do 44 because I remember doing that in homework. So that one I should, yeah, I think I can do that one. We'll change the color though, at least we'll keep things fresh, dark yellow. So if you want to find the angle theta, the way you do that is by using this property. Specifically, the property does not, okay, whatever. Magnitude of r of t times the magnitude of r prime of t. And so, what is r of t for this one? For either of them, it doesn't really matter. We can do it for, yeah, I mean, you can do it for whichever one of these you'd like. And there isn't really much of a difference. It's fine. But we'll do it with 44. Okay, so before we just start plugging, so okay, so what would this give us? Let's just be thorough. It'll give us theta is equal to cosine inverse of this whole thing. And I know there are a lot of lines and lots of stuff here, so just if I miscounted and I put like too many lines or too few lines, don't worry about that. You get the point. Anyway, r of t is t squared and t. So what is r prime of t? 2t and 1, which means r prime of t, sorry, r of t dot r prime of t is just equal to 2t cubed plus t. This is what we have now. What's the denominator going to be on the other hand? It's going to be the square root of, well, t squared plus t to the fourth. That's one of them. This is going to give us 4t squared plus 1. It's another one. The numerator is 2t cubed plus t. Are we given something about t being greater than 0? We're not. Can we do anything about that? I think, isn't t supposed to be greater than 0? I'm not fully sure. The point is that the arc cosine of this is theta. So what's that going to be? This is t times 2t squared plus 1. This is t times the square root of 1 plus t squared times the square root of 1 plus 4t squared. Maybe there's some algebraic property to simplify that. I don't know. I can't think of anything right now. I mean, you can multiply them, but there's no need to do all that. I think we're fine like this. I'm thinking if there's anything else that can be done. Oh, yeah, obviously cancel these. Only problem is I don't know if it'll be positive or negative, right? So that kind of changes things. Like, I don't know. Find any values of t. And yeah, I'm not going to do the rest of it because it's graphing utility. And I don't think you're to find any extrema and to find any values of t where they're orthogonal. So you just want cosine of that to equal 0. So this will have to be like, what, pi over 2? Sorry, no. No, wait. Well, okay, you're just equating this with 0, so t equals 0 should do it. And then, I mean, like, that should work. I don't know what else will work because you want cosine of theta to equal 0, right? So yeah, I mean, that's all I can think of. Then maybe there are other values. Maybe they're referring to that in the context of 43, where there might be more. I don't know though. But that's so it's basically the same stuff. We found r of t, we found r prime of t, did the dot product. We all of those things we've done very often already in this stuff. Okay, the next one is kind of like it's basically it's almost exactly what you might have done in calculus 1 when you were going to learn like the definition of a derivative and how to get there. It's basically the same thing. It's using the limit definition of a derivative to actually find the derivative, right? And there are four of these questions with a total of what, 8, 9, 10, 11, 11 different components. So unless you plan, some of them are obviously easier than others. So let's just do the easier ones because I trust that you can, figure out the rest of these yourself. We'll do this in, let's find a custom color. Let's do like nice purple, bluish purplish shade. Too dark. I'll make it a little bit bluer. Let's just go for full blue and see. Um, let's try 46. This will be fun because there's like a bit of diversity. It's not just polynomials. It's not just zero, right? There's some, and it's not trigonometric. There's some fun stuff in here. So let's figure it out, right? Each component. Actually, no. There's a way to do this. So you'll do the limit of r of t of r of the limit as delta t tends to 0 of, wait, 1 second, let me restart this. You're going to do the limit as delta t tends to 0 of r of t plus delta t vector valued function minus r of t divided by, I sound very slow while I'm doing this, but like it's just making sure I'm doing it all right. Okay, let's just write r of t in case we scroll too much. Again, I'm not going to write I, j, and k, so I'll just do it like this instead. Well, we will have to do some I, j, and k here. Like we have to use that notation. Okay, so let's begin. What does this tell us? Well, what is this going to be? What is this actually going to be? We do have to plug it in, right? So we're going to get the limit as delta t goes to 0 of, and then this is going to give us square root of t plus delta t I plus 3 over t plus delta t j plus, well, minus 2 times t plus delta t k. That's the first one. Now we're subtracting off this big thing here. Well, that's easy enough. Root 2i plus 3 over t j minus 2t k. Perfect. And what are we dividing this by? Nothing but delta t. So I'm going to zoom out a little bit, let you soak all that in. Now we go for the fun part. We just rearrange our terms here. So same limit, same everything. Now we have t plus delta t minus root t I all over delta t again plus 3 over t plus delta t minus 3 over t j minus 2 times, now we get, well, wait, what? Yeah, t plus delta t minus t k. Okay, fine, that's easy. Now we break this up into three limits by using the property, this addition property of a limit. This is the first one. Square root obviously extends until here. There's an I. We can also take out the I, right? So we can just put that out there. Now we have this one. if you're getting bored by this, let me know in the chat and I'll skip this one because I can't imagine you guys are enjoying me do all this long lengthy work. If you are though, that's completely fine. This one is particularly messy because there's like three layers here, and then what's with k? It's going to be, you can take out the -2 as well, just like you can take out the k, and this is t plus delta t minus t over delta t. Looks like an at. This is delta t and then k right there. Okay, okay. If you get the pun, leave a like little thumbs up in the chat if you like the joke I made. But now we can start to simplify stuff. Hopefully you recognize the third one over here. This is -2 times the limit as delta t goes to 0 of delta t over delta t, then k, which is just -2k. So this one is done. What about this one? This one seems long and messy. Sorry, long and messy. And it is. It's 3t minus 3t minus 3 delta t all divided by delta t. So okay, this is where it gets messy. So just follow along. If you have questions, ask. But it's going to be, so it's going to be delta t times t times t plus delta t. And so in this, you're going to, uh, yeah. Okay, so we're going to continue here. This is just -3t. This is -3 delta t over delta t times t times t plus delta t. So it's very messy. And just to be clear, you're still doing the limit as delta t goes to 0. And there's still a j at the end as well. All that stuff still applies. Right? It's not going anywhere. This cancels with this. So we're left with -3 over t times t plus delta t. And now you might think, oh, we're done. I mean, oh, we're not done. What do we do now? We've got a delta t. That's why we're taking the limit as delta t goes to 0. And usually, if you see something in the denominator, you'll say can't go to 0. But here you can because that's not causing any trouble. And so this would just, and then there's a j here. This would be -3 over t squared j. And if you know how to do derivatives, you'll see that this is indeed correct. Like it checks out. So we're done with that one now. What about this one? Let's try it out. This is like, you can probably guess the method and then you just don't want to do it. I can't blame you. It's an annoying one. It's rationalize rationalizing, or yeah, something like that. So we'll do t plus delta t minus t minus root t, and I'm going to multiply it by its conjugate. The reason for this is that, well, you'll see. We're going to get a delta t in the on the top, okay, from a difference of squares. But if you multiply the numerator by something, you do have to do the same with the denominator as well. And so we're going to do just that over here. Okay, and hopefully, actually, if you haven't done limits before, on the bright side, if you haven't done derivatives before, I was throwing around the fact that um, I was throwing this around, right? Now you'll actually be able to see why that's the case. Right? So hopefully this is at least of some use to some people. The numerator becomes t plus delta t from the difference of squares minus t. The denominator now is delta t times square root of t plus delta t plus delta t. This cancels out with this. This cancels out with this, and we're left with 1 over, again, obviously all the limit stuff, the limit as delta t goes to 0 is still there. It's just that I'm not writing it out because it's a lot and there's no space here now. So this is now the limit as delta t goes to 0 of 1 over and then of course we can't forget the I over there. Now that we've got all these, which is been a real I opener, we'll just get 1 over 2 root t, -3 over t squared, and then what's the last one here? -2. And with that we're done. Very long, like this is what actually, let's actually compare. This has probably been our longest question so far, except for obviously 39, because there we had like 5 different steps. But this was one of them. There are 4 of them. So I could have done this for all of them and wouldn't have, it would have just been tedious and a waste of time for everyone, I think. So no need to do that. Let's now move on to these indefinite integrals. And I think we're actually going to call it a day here. After 50, we might do the definite integrals and then until 68 as well, right? Because like I'm starting to get a little bit tired and I do have a fair bit of homework left myself as well. So I think it's best that we just kind of end things after. Actually, we'll see how it goes. None of these are particularly hard. One thing that I'll give a quick tutorial on this. Um, so when you're doing it with scalar valued functions, you always get a scalar constant of integration, right? Over here, you're going to get a vector constant of integration. That's the big difference here. And so to show you what that means, we'll just do some examples. No, we won't. So when you, the way you do indefinite integrals and definite integrals is by, I'll zoom in here because it's just me talking now. The way you do definite and indefinite integrals with vector valued functions is component wise, right? Just like we've been doing derivatives component wise, limits component wise, everything component wise, same thing over here. And so each of the components is itself a scalar valued function. And if you're integrating that, if you're integrating a scalar valued function, you're left with a scalar constant of integration. Now imagine a scalar constant of integration. So it's not a it's a scalar valued function, but it's also a scalar constant. It's just a scalar, right? Like 3t or 3x is a scalar valued function, but it's not a scalar in itself. It's a scalar valued function. This is still a scalar valued function, just like y equals 3. 3 is a function, right? It's a very simple function. It's a constant, but it's still a function, right? So ignoring all that, you're going to have one constant of integration each of the different um, in each of the different directions, and that's going to form a vector with well, like functions within them. So it's a vector valued function, and that vector valued function is usually, actually guess, right? Like usually when you write constants of integration, it's c1, c2, etc. So when you have a vector valued function, once you're finishing that off, you're just going to put c with a vector on top. It's the c vector, and that's kind of your con um wait, I'm blanking, right? It's your constant, it's your scalar valued function of integration. Sorry, it's your vector of integration, not your constant of integration, because it's constants in each of the components. So it's just going to be like, it'll be something like 3 4 5, for example, right? And I've spent a lot of time talking. Let me just like show you with some examples now. Sorry about that. I think the lack of sleep recently has been catching up to me. So we'll take pink. Let's do 49. And so I'll zoom in a little bit. I'll just like shrink this. One sec. I want to make save some space here. Let me know if you can see everything fine, because I know my video is at the bottom and it hasn't, I mean, I haven't heard any complaints or issues regarding that, but in case there are, please do let me know. I'll fix it. It's not hard to fix at all. Let's do 49. So we're going to integrate 2t with respect to t. This is going to give us t squared plus c in the I direction. We're going to integrate 1 dt, which gives us t plus c1 in the j direction. We're going to integrate 1 dt, which gives us t plus c2 in the k direction. So, I'm speaking very softly. I see where the problem is now. But okay, so you can now see that c, no pun intended, you have t squared, t, and then t over here, plus, right? Because we can do this with vectors, c, c1, c2. You don't have to call them c, c1, c2. You can call them c1, c2, c3, anything you want. The main idea though is that this is t squared, t, and then this entire thing is just the instead of the constant of integration, it's the vector of integration. Maybe that's not the official name, but it sounds nice to say, so I'll just stick with that. Let's try 50 now. So similar idea. We're not going to write it out like this each for each component. We're just going to integrate term by term. What's the integral of 4t cubed? What's the antiderivative? Ignoring the constants, it's just t to the fourth. This one will be 2t cubed. This one will be negative 8 thirds t to the 3 halves. Reverse power rule. And then we add a vector of integration. What about 51? Natural log of t, um, negative 2 fifths t to the 5 halves plus c. What about 52? 52 is this one I remember because I did the proof myself. It's not a hard proof or anything. I just did the question myself once. T natural log of t minus t. Now, if I get that wrong, that's going to be pretty shameful. But I think it's no, I think that's correct. Okay, the second component is again same thing. Lots of ways to save time over here. You don't have to do everything. And then t again, right? So there's not much difficult math or integration required here. You just need to understand the concepts. Like, don't write c, write c with an arrow on top of it to indicate that it's a vector. Small things like that. None of them are like really big deals or anything, but just might be useful to keep in mind. 53. What is 2t minus 1? That's going to give you t squared minus t. What's the antiderivative of 4t cubed? We did that exact one. It's t to the fourth. And then 3 root 2 will be 2 times t to the 3 halves plus c factor. 54. I'll do that over here to save some space. E to the t, and then here we have negative cosine of t. This sometimes I think gets people confused, like because you're used to seeing the derivative of sine being cosine and then the derivative of cosine being negative, but it's opposite over here, of course. Right, the integral of cosine is going to be positive sine, the integral of sine of t is going to be negative cosine. But yeah, just don't mess that up, I guess. Here, okay, this one is nice and easy to recognize because for me, I don't know why it's easy for me to recognize. I think it's because it satisfies this t squared plus 1 equals d. Oh, well, no, like it satisfies this equation. I think. Yeah. Okay, this makes me sound really stupid. Like, oh, I remember it because it satisfies that equation. No, it's just that it's like it seems nice to me. It's the point is it's tan of t, right? I just like that it goes to secant square of t, and then there's a nice property with secant and tangent, so it just seems very convenient to me. And then even more convenient, this is arc tan of t, so there's a very nice looking vector here, but doesn't matter because you just add a plus c and then we're done. 56. This one's a little. You just need to be careful of the minus. Actually, no. Uh, this one's this one's a little bit harder because you have to integration by parts twice to get either of these. But I think I know how to do it. Like, so you'll have this um, with a sine of t, and when you integrate this, I mean when you differentiate this, you're going to get e to the negative t sine of t, and then you're going to add or you're going to subtract negative you're going to subtract e to the negative t cosine of t. And so to account for that, what you want to do is add e to the negative t cosine of t. It might be better to just do the integration, but I actually kind of forgot, and I don't want to do it with all the negative signs. I think it's a better exercise to think this through logically. Um, so we know that, well, okay, let's just do it. This is going to give you e to the negative t sine of t plus, or well, I guess minus e to the negative t cosine of t. So here you would also want that to be a minus, actually. Yeah, yeah. So, okay, so I got it now. This will be a minus, and then you divide the whole thing by 2, and that will give you the first one. If I did this properly, I'm sure I could have done it faster than it would have taken to do it with integration by parts. Very similar thing for the second component, I think. It'll be, so you're going to have negative e to the negative t cosine of t. And then I think you're now going to have plus e to the negative t sine of t. And the reason for that is that you'll have, oh, wait. Yeah, and then you divide this by 2. And I think that's it. And then obviously that's not it. You have to add this as well. But I think that's it. The integration might be wrong there, but I'm pretty sure I recognize this, and so this should be correct. It feels right to me, so we're going to stick with this. But yeah, that's it. Like for all these indefinite integrals, it's very, very simple integration of um, each component. Evaluating definite integrals, it's the exact same thing, and then all you add on at the end is essentially the, I mean, you evaluate the integrals and you subtract them. And so your answer for all of these should be, actually, try to guess, right? Like, is it going to be a vector? Is it going to be a scalar, vector valued function, scalar valued function? It'll be a vector because you're getting, just like when you integrate normally, you get a scalar, right? You get a scalar. And I think I mentioned this in one of my videos, not this live stream, like the last video I made, that when you're going from a vector to a scalar, you can like literally just, a vector valued function is a scalar valued function. A vector is a scalar is a vector, vice versa, right? You just literally just change the words. And so just like with integration, when you have a scalar, here you'll have a vector. And the reason for that is that in each component you'll have a scalar, but they're different components, and that forms a vector. And within each of those components, you don't have a function, you just have a constant. So it's constant, 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 and that makes a vector, which is still a vector valued function, but it's better to describe it as a vector because that's more specific. We can do these definitely, but it's just that they'll be a little bit messy to do. Like, okay, we lose 62. We'll evaluate this one because this one is probably the hardest one, right? That's why it's at last position. Just so you can see how it's actually done. But the other ones are like all very, very similar. It's basically how we did these indefinite integrals, except you're plugging in values, right? And that's not something that's super important, right? You just need to understand how it works. And I don't think my plugging in and then probably getting it wrong is going to help anyone. So let's do this instead. The first thing they're doing, they're basically they're giving us this magnitude, right? And what does this magnitude mean? It it means that you're making this a scalar. And because you're making this a scalar, now it's now like a regular integration that you're forming. Because it's a regular integration that you're performing, you're going to get a scalar as your answer as well, right? Now it's just a normal function. And what is that normal function? This is the question that I was referring to earlier when I said there's a square root in it as well. What do you get here? Um, let's find out. So that it's going to be this. It's going to be t squared plus t squared squared, which is t squared plus t to the fourth square root of that, which is and now these are things that a little bit, just be a little bit careful of what you do here. It's t squared times t squared plus 1, which is nothing but true or false. This is t square root of t squared plus 1. Now, usually you'd say no, it's absolute value of t, but over here, because we're going from 0 to 3, we know that t is greater than 0, so we can just leave it like this. And this is very nice because we can do some u substitution. Dt. So the u substitution that makes the most sense here is like u equals t squared plus 1, and this would give us du equals 2t dt. So dt equal, I mean, there are enough ways to do this, but this might work out. Hopefully, maybe you'll enjoy this. What would the bounds go to, by the way? 3 would go to 10, and 0 would go to 1, plugging it into this formula, going from here to here. So anyway, let's see what we get now. We're going from 1 to 10. We have t. It looks ugly that there's a t here right now, but we'll get done with that soon enough. Du over 2t. I'm trying to be very methodical here. Okay, what do we now? Look, we can keep scrolling because we don't need any of this old information. It's dead to us now. We know we've already converted in terms of u, and so we're done. There's nothing else to worry about here. It's 1/2. This is maybe a little bit easier to just see it like this in this form. Okay, we can take cancel out a little bit, so we get 1/3 u to the 3/2, and because I bounds, it's 10 and 1, and um, well, that's 1/3 u root u, right? I think 10 and 1, so that's going to give you 10/3 root 10 minus 1/3. We can, I'll break my no Desmos policy and then like try it out. Oh, 1 second. I accidentally added some other stuff to the border. We just get rid of that. Wait, no, I don't want to open it here. Let's see. Let's check with Desmos because I think this should be correct, and if it is, this could be a nice problem to end off on as well, since it's quite tough. See, integral from 0 to, no, mm, well, no, wait. Yeah, it should be this. What did we get? We got 10/3 square root of 10 minus 1/3. Exact same thing, perfect. Nice, neat answer. I mean, no, not a nice, neat answer, but nice that we got the right answer. That we got the right answer. So, okay, let's see now if there's anything else that's interesting here. This is this is very similar. This one is you integrate it twice. It's kind of like when you're going from acceleration to velocity and then from velocity to position and then plugging in the given conditions. Same exact thing with 66. So 65 and 66 are like brothers over here. 67 is this isn't hard to integrate, otherwise I would be tempted to do it, but it's just u substitution. In fact, it would be -1/2 e to the negative t squared plus c. That would be integrating that, and so does not particularly matter. The last one, 68, is r tan of t, -1 over t, natural log of t, so on. So just plugging in. So nothing very difficult or particularly challenging in any of these, really. And we did 62 here already. These are all proofs, and these proofs are kind of annoying because they, like, I had to do these in class and they take very, very long. You have to write out all the components, evaluate the cross product, um, and then I think after that you do the dot. After that you apply the product rule, and then you rearrange everything and then take it back. So it's basically the properties that were mentioned earlier that I kind of went over to as well. But then it's a lot of work with them, and that work is not enjoyable to do at all. It's like the limit stuff on steroids because it's just so much. Um, so this would be the tangent vector. You'd find the derivative by taking the derivative of each of the components. You can also use the limit definition of the derivative like we showed with one of those questions. The limit as delta t goes to 0 of r of t plus delta t minus r of t all divided by delta t. So that's one way to do it. But yeah, like generally you just do it component wise, like you do almost everything that we've discussed in this chapter: differentiation, limits, integration, etc. geometric interpretation, again, it's just a tangent vector. How do you find the integral? Well, you just integrate each of the components of the vector. The three components of the derivative of the vector valued function u are positive at t equals t sub 0. Describe the behavior of u at t equals t sub 0. It's increasing, it's pointing in the positive x, y, and z directions, right? Because it's going to keep, the tangent vector is pointing, okay, the tangent vector is going to be in the first octant, right? If you like give it a starting point of 0 of the origin, 0 0 0, because it's positive in all directions, so it's increasing in the x, y, and z directions. That's all that means. The z component of the derivative of the vector valued function u is 0 for t in the domain of the function. What does this imply? It means that you're at a fixed location on the z plane, right? Like on the, so your base, everything is basically on the xy plane for some given value of z. So it's like flat, right? Whatever the height is, we don't know if the height is 0 or not, because we know that the derivative there is 0. It might be moving around doing anything on this plane, but it's on like a particular plane, right? Every point on it is going to be coplanar because the z component is 0. And so yeah, it's basically just a vertical translation of the entire xy plane, and that's where the vector valued function u is. These are the proofs. We're not going to do those. Not going. This is graphing utility. We're not going to do that. And then this one is, what is the curve? The curve is going to be, oh wait, I know how to do this. The curve is going to be an ellipse. If you just set x equal 2 cosine of t and then y equal 3 sine of t, you'll see that x over 2 squared, x over 2 whole squared plus y over 3 whole squared is equal to 1. So it's a vertical ellipse with semi-major axis 3. So semi-major axis 3, semi-minor axis 2. So it's like this, like this. Find the minimum and maximum values. For that, you would just, so okay, it'll be, r prime would be negative 2 sine of t, j plus 3 cosine of t, k. So it'll be 4 4 sine square t plus 9 cosine square t, which would give you 4 plus 5 cosine square t. And then the minimum value of that is going to be the square root of 4 plus 0, which is 2. Maximum value would be the square root of 4 plus 5, which is square root of 9, which is 3. Same exact thing for r double prime. You'll just get it in a different way, but the minimum will still be 2, maximum will still be 3. So that's it, I believe. True or false? If a particle moves along a sphere center at the origin, then its derivative vector is always tangent to the sphere. I don't know how to prove that, but I think it's true. And they're not asking you to do it, so yeah, it's true. Definite integral of a vector valued function is a real number. It's not a real number. It'll be a real number in each of the components, which means it's a vector, just a plain simple vector. 85. The magnitude of the derivative of the magnitude of r squared is equal to the, I don't think that's true at all, because like one of them is, yeah, that doesn't make sense. I think we did an example earlier, but that's not the case. But there's no, you're taking the magnitude, so r of t, the magnitude of r of t is always going to be positive, and it's going to be a number, and so that number is going to have, no wait, like for question 82 this would apply, but I don't think in general it has to apply. I might be wrong. If you guys have any ideas, like comment them for question 85, this one over here, because I'm not sure at all. I don't think it's true. I've got a strong hunch that it's not true, but I just don't know how to prove it. 86 is incorrect. 86 is incorrect for the reason that it's instead, it's r prime of t dot u of t plus u prime of t dot r of t. We know that from the property, and that one was something that I proved myself, so I'm confident in that. Consider the vector valued function So to show that they're always perpendicular to one another, you'd find r double prime of t, and that would be a little bit messy to do, but it's actually I don't it wouldn't be that bad. You find them and then you take the dot product and then you show that the dot product is equal to zero, which probably won't be hard, like if you actually do it. That's it then. Next one is velocity and acceleration. And eh, actually this chapter, the way this book is designed is different than I would have thought. So this we're going to go into like curl and like actual multivariable calculus stuff later on in this very section, I believe. And so like in this very chapter. But until then, yeah, that's it. So we did like we probably did like half the questions, but that's still quite a lot. And it's been almost 2 hours that we've been solving these questions. So I think that's a lot of time that we've put into it. Hopefully you took away something from the video. Hopefully you enjoyed it. Thank you so much for watching. If you enjoyed, I'll try to make more of these when time permits. So um I'll probably make one for 12.3. I might go back to chapter 11 and revisit some of those topics as well. Yeah, no worries, Anoop. Hope you enjoyed. And then besides that, I'll try to make some more physics videos as well in the future. I don't have like a physics PDF like this, and I'm not good enough at physics right now to be, you know, showing all solving so many questions all hopefully all accurately. So I'll keep on working on those skills, but I should be able to at least make some sort of interesting physics videos soon. Like I was making some on the H.C. Verma book, for example, which I've been reading and working through. I'll try to put more questions from there and solve those as well, but they won't be like long live streams like this. So it won't be um, kind of non-stop teaching and reciting. It'll just be short videos, and there's like a batch of like 6 or 7 IIT JEE videos that I've made as well. I haven't uploaded them yet. I'm saving them so that they can like do better, hopefully closer to the exam date. But I'm making more videos right now. So if you're new to the channel, like I used to make a lot of videos earlier, but then because of school and other things, I kind of stopped. But I'm getting back into it now. The editing and everything might be a little bit worse because I'm spending less time on it, so I can make more videos. But um, but yeah, so if you have any suggestions for what I should make or what you think might be more useful, please do let me know. Like just comment it on any video or or any of the discussion posts or whatever that I make, and we can, I'll definitely take your advice into account because I make videos for my audience, right? That's the entire point of this. So yeah, that's it. If you have any questions or anything or any suggestions, just leave them in the chat. I'll go and do some of my other homework, but I'll just stay in the call for like another minute. I'll stay in the live stream for like 2 or 3 more minutes, and um, then we'll call it a day. Okay, if there are no more comments, suggestions, anything like that, then I'll just end the meeting now. End the live stream now. Thanks so much for watching. Hope you enjoyed.